In this module, we are going to continue with where we left last time, which is acceleration of a fluid particle, and try to complete this and hopefully go to Reynolds transport theorem and complete the same. We said that unlike a solid, fluid is very different because position of the fluid particle is important, and we took the conventional example of nozzle. This is something which we have to tell students. Steady state just does not mean no acceleration in fluid mechanics, because nozzle steady state there is definitely an acceleration, which means change in velocity. So, if I take a snapshot of the velocity at this location, it is always going to be v1, it is always going to be v2 here, whatever time. Velocity is changing with respect here with respect to position, but with respect to time, velocity here remains v1, here it remains v2, everywhere whatever is the velocity at a given cross section, that remains the same, and therefore steady state by our definition is valid. But we are definitely sure that there is an acceleration here, and that is what is seen from this derivation that we are going to do. Any flow field, you have velocity is a function of x, y, z and t. So, I could have something which is particle which is at a position 1 goes to position 2, and with respect to coordinate axis, this could be x, y and z, and this could be in random plane. This could be x1, y1, z1 at t plus delta t, this could be x2, y2 and z2. Not necessarily along in the yz plane or in the xz plane or in the xy plane. This could be, imagine it in 3 dimensions. You can give the example of the classroom. You have a particle which is at the corner there, and it is moving in a particular direction, which is very random. So, each coordinate x, y, z is going to change with respect to time. So, if we are talking of point 1 or point A, if I call it, so V in general is ui plus Vj plus Wk. Each of this u is a function of x, y, z and t. V is a function of x, y, z and t. W is a function of x, y, z and t, isn't it? So, 3-dimensional unsteady field. So, we can write this velocity for a fluid particle at position A by giving x a, y a, z a, or x, y, z just for simplicity, and then we will say V of A is nothing but x function of x, y, z and t is nothing but u of A at x, y, z and t I cap plus V of A x, y, z and t j cap plus W of A x, y, z and t k cap. This is your velocity at that x, y, z location. Now, let us write it for, this is at time t, at time t plus delta t. At time t plus delta t, it has moved from x to x plus dx. Delta x could be 0 for all you care, but in general Va would now be x plus delta x, y plus delta y, this could be negative also, z plus delta z, t plus delta t, and therefore, this is going to be u of A x plus delta x, y plus delta y, z plus delta z, t plus delta t I cap plus similar thing delta x, y plus delta y, z plus delta z, t plus delta t j cap, w x plus delta x, y plus delta y, z plus delta z, t plus delta t k cap. Okay, I have not done anything. I have just written the velocity vector at this new position x plus delta x, y plus delta y, z plus delta z. Okay. So, we can drop off this a because any random particle you can just say it is just a function of the local position and the time. So, if I want to say, if I subtract equation 2 which is written in purple from if I subtract equation 1 here which is velocity at time t from equation 2 which is velocity at time t plus delta t, this is equation 1, I would get 2 minus 1 is nothing but v x plus delta x minus y plus delta y, z plus delta z, t plus delta t minus v x, y, z and t. This is what I am doing, this divided by delta t. I am subtracting the left hand side and the right hand side, I have to write the right hand side term. This is the left hand side. Can I write this as dv by dt, right? So, this is my left hand side. Right hand side would be subtraction of ua at x plus delta x, y plus delta y. So, this term minus this term minus this term, all a's I have dropped, this term minus this term. So, simply it is going to be my definition of the derivative, f of x plus h is equal to f of x plus h times f prime of x plus higher order terms, correct. So, f of x plus h minus f of x divided by h is equal to f prime of x, or f of x plus h, that is this term, minus f of x, that is ua, is nothing but h f prime of x. What is this? Du by dx into delta x plus du by dy into delta y, change in y, du by dz into change in z, du by dt times change in time, right. 4 dependencies, 1, 1, 2, 2, 3, 1, 2, 3 and this is time part. So, like that you will write for v, like that you will write for w. I am just going to do u one by one. So, this is u of x, y, z and t I cap plus this is v of a x plus delta x, y plus delta y, z plus delta z, t plus delta t. I am writing this equation 2 again in these terms which are expanded form, plus du by dx delta x plus dv by du by dy delta y plus du by dz delta z plus du by dt delta t I cap. Okay. This plus v x y z t j cap plus dv by dx delta x plus dv by dy delta y plus dv by dz delta z plus dv by dt delta t j cap plus w x y z and t k cap plus dw by dx delta x plus dw by dy delta y plus dw by dz delta z plus dw by dt delta t into k cap. This is equation 2. Now, right hand side equation 2 minus equation 1 divided by delta t. Equation 2 is this one. I subtract right hand side of equation 1 which is nothing but u, this first term, this one, this one, this one. So, what is left is only this, this and this. So, I am going to be left with right hand side is nothing but du by dx delta x, I am dividing by delta t. So, that comes here du by dy delta y by delta t plus du by dz delta z by delta t plus du by dt. This is my first term I cap plus dv by dx delta x by delta t plus dv by dy delta y by delta t plus dw by dz delta z by delta t plus dv by dt j cap. Third term would be dw by dx delta x by delta t plus dw by dy delta y by delta t plus dw by dz delta z by delta t plus dw by dt whole k cap. We are done. This on the left hand side was dv by dt. Okay. What is this quantity? What you see here, delta x by delta t is nothing but the x component of the velocity. This quantity that you see here is the y component of the velocity. This component, this thing that you see here is nothing but the z component of the velocity. Therefore, the dv by dt therefore, I have dv by dt is nothing but acceleration of the particle is given by u into du by dx plus v into du by dy plus w into du by dz I cap plus du by dt I cap plus u into dv by dx plus v into dv by dy plus w into dv by dz j cap plus dv by dt j cap, and third term u into dw by dx plus v into, this is u, v into dw by dy plus w into dw by dz k cap plus dw by dt k cap. Okay. This first term written in blue is given the definition du by dt. This is given dv by dt and this is given dw by dt. This is acceleration x component. A sub p is ax I cap plus ayj cap plus az k cap. X component of the acceleration, y component of the acceleration, z component of the acceleration. Anything with I cap is grouped together, that is the x component of the acceleration. Anything with j cap is the y component of the acceleration. Anything with k cap is the z component of the acceleration. Remember, this is written now as du by dt I cap dv by dt j cap plus dw by dt k cap. This derivative d by dt is called as total material or substantial derivative. It is not a single term. It is a group of 4 terms where there is a definition of the derivative with respect to t, definition of derivative with respect to the space coordinate. This is an operator. Capital D by capital dt of any variable is nothing but d by dt of that variable plus u times d by dx of that variable, v times d by dy of that variable, w times d by dz of that variable. This is the definition of the material derivative. So, when I put this bracket as u, I get the first term. When I put this bracket as v, I get the second term. When I put this bracket as w, this bracket here, I get dw by dt, which is the group of third term. So, I hope you are able to see this. So, what is, let us look at each term one by one. Du by dt is nothing but total or material or substantial derivative of the x component of velocity. In solid mechanics, we were not worried about change in velocity with respect to position, because solid by definition, every particle is going to be at the same position relative to its neighbor at a different location also, unless you have crossed the elastic limit. In fluid mechanics, this not being the case, you have change in velocity with respect to time. I am going to write only for the x component. We will relate everything to the x component and then say that just as this you would have the y and z component. This is nothing but du by dt, change in x component of velocity with respect to time. Okay. So, it is just x component of velocity was 2 meter per second, at next instant of time it is 2.1 meter per second. That is this change with respect to time, very simple to understand. Okay. So, it is a car driving, you are driving at 55 going to 60 in next 1 minute. So, you are accelerating, that is this part. What is this other part? U du by dx plus v du by dy plus w du by dz. These are the important terms. This one is as if the x component of velocity is being changed with respect to position, nozzle. When you go back to your nozzle example, the position of the particle is changed, the velocity has changed, right. So, position is changing. Okay. This is unique to fluid mechanics, this bracketed term. This is called as local acceleration. This is called as the convective acceleration. Convective acceleration, as the name suggests, is where the particle is changing its velocity not because there is a change in the magnitude with respect to time, it is because its position is changing. So, when the particle has moved from position 1 to position 2, by virtue of the change in position, the velocity, x component of velocity has changed. By virtue of change in position, the y component velocity has changed. By virtue of change in the position, z component of the velocity has changed. That is given by this. Where did this come from? It came from this part which was written as delta x by delta t. This part was delta y by delta t. This was delta z by delta t. Remember this? This is change in the position delta x by delta t. Okay. It is as if the change in the velocity in the x direction. Remember one thing, this is all related to x component. I am writing du by dt. This is not d capital V by dt. It is the whole thing written for acceleration in the x component only, ax, x component of the acceleration. That means what all changes are possible to the velocity in the x direction. What is the direction, x direction velocity? U. So, we are worried about change in the velocity, x component velocity u with respect to time, change in the x component velocity with respect to space, x direction, change in the x component velocity with respect to space, y direction, change in the x component velocity with respect to space, z direction, because 3-dimensional. We have not worried about y component at all. That will be a different equation. So how do you make students understand what change you are talking about? X component velocity, that has to come in the derivative dependent variable time x, y, z. The bracket or the argument for that thing would be u, 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 u. Okay. Now what are these u, v and w? These are like the carriers. These are what are taking these changes along with them. X component velocity change because of the change in the x coordinate is transported, is being carried by the x component of the velocity. Is that a fair statement? You're getting down from a crowded local train in Bombay. You want to, this is the direction of the train is going from right to left, the train stops and you get down this way and you want to go actually back because the bridge is on the back side. But because the whole crowd is going this way, you are wanting to go this, but you are being pushed in this direction. These terms are like that only. X component of velocity change with respect to position is being carried in all possible direction by the x component of the velocity. You change in x component with respect to y, that means it has the y coordinate of the new position is different from the y coordinate of the old position. Therefore, the x component velocity has changed. Therefore, du by dy exists. Who is carrying that effect? That is the velocity in that direction. Please remember this. U with respect to x here, v is with respect to y, w is with respect to z. X momentum x component of the acceleration. So everything here is for u. The carrier and the coordinate with which you are taking the derivative will all be the same. U with respect u du by dx, v du by dy, w du by dz. Change with x component of velocity due to change in position. This part is what is non-zero in a nozzle. Du by dt is 0. I can write this for dv by dt. This is d small v by dt plus u dv by dx. Please remember, when this is u, this is x. Y component, therefore small v. V dv by dy, w dv by dz. This is a y. dw by dt is nothing but dw by dt plus u dw by dx. Change in the z component of the velocity with respect to x. It is being carried by the x component of the velocity u, therefore multiply v dw by dy plus w dw by dz, which is equal to az. These terms in the square brackets are non-zero for flow in a nozzle or a diffuser. So, local acceleration may be 0. Convective acceleration will be non-zero in case of flow through a nozzle. Therefore, the acceleration of a fluid particle is there. What is this? This is basically the left-hand side is you are trying to follow that particle. Remember, you followed that particle. So, this is your Lagrangian viewpoint. Following a particle. This right-hand side is the Eulerian viewpoint. Okay. Material derivative represents a methodology to transfer from Lagrangian viewpoint to the Eulerian viewpoint. I want to relate these two. I want to see if I am taking a particular control volume. At initial time, the control volume and the system are the same. By that I mean there is a certain mass at a given instant of time in a control volume, which is there. That has taken some heat, some energy. When some part of it leaves, it takes away some energy with it. I am interested in what happens to that. As it leaves, fresh amount of air or fluid, whatever it is, comes in. So that is bringing something different or same, I don't know, but it's bringing something. Something has left. That something originally was part of my system. I want information on that, how it is affected, because what has left is also important than what has come in. So if I am having three modes of money coming into my account and only one mode of how it is being spent, then it's easy. But if I have money being spent differently by through credit card, through online auto bill debit, so you have multiple ways in which money is spent. Credit card bills you will pay, electricity bill is auto debit, phone bill is auto debit. So each of these you take care of. Like this, the Lagrangian and Eulerian description are important when I have to take care of what is part of the system when it becomes part of the control volume and is also going away because of the mass flow associated with it. This very important concept is what is called as Reynolds transport theorem. It will relate the Eulerian and Lagrangian viewpoint. In the next module, we will derive the expression for Reynolds transport theorem, which will be used for derivation of conservation of mass, momentum and energy. Thank you.